Hey everyone, in this video we're going to be showing that the quadratic formula works. Now, this problem can be found in your free online complex analysis textbook, which can be found in the link in the description below. This is problem 1.7. So let's be more specific. For a, b, and c that are real numbers, with a being non-zero, prove that the roots of the equation az squared plus bz plus c equals 0 are... and then there are two answers here. Now, I like the framing of this problem because this right here has a special definition for when b squared minus 4ac is negative, and it's defined to be specifically this right here. Now, you might wonder, wait a minute. I thought whenever I have something like -4 in a square root, I thought I could just make this positive 2i. Right? Can't I just do this? No. Please stop doing this. Don't ever say this. Just don't. Because it's not true. That's not true at all. Just absolutely wrong. So anyways, the point is there are multiple problems with defining I as the square root of negative numbers. You can't take the square root of a negative number. So the concept of the square root of -1 is as unfamiliar as the square root of a cat. Those two things are equally confusing. If you think one is more confusing than the other, then you are brainwashed, I guess. You've been convinced of a lie. You've been deceived. That's okay though, because we're not going to run into this problem. Not in this course. In my videos, I try not to make those kind of mistakes. Those are pretty big mistakes to make. And unfortunately, YouTube is chock full of them. And none of them really wants to understand why it is that -1 doesn't equal 1, despite the fact that -1 is I squared, which supposedly is the square root of -1 times the square root of -1, which, I mean, by properties of the square root function, is the square root of -1 squared, which is the square root of 1, which is 1. Yeah, red flags. What happened? Again, that's problematic. And that's problematic. Both problematic. This property, this algebraic property here, doesn't exactly hold for when the inputs here are negative. They only hold for when the inputs are non-negative. And then this equality just doesn't hold because I is not the square root of -1. That's not I. I is just the unique object that we just created in such a way that if we square it, we get -1. Does that mean that I is the square root of -1? No, it's not. Okay, so let's try to prove this theorem, that the quadratic formula works. Now, I see a lot of YouTubers start off by writing az squared plus bz plus c equals 0, and then they say, now let's try to solve for z by like completing the square. And there's a huge problem with these videos. Massive, massive problem. They are using circular reasoning. If I start by writing this, within like the first 3 lines of this proof, I'm using circular reasoning. I can't just say that this is true when A, I haven't instantiated z, and B, if I did instantiate it, then just writing that out would be a conclusion, a statement. And making that statement would conclude the proof, which begs the question, where's the work? So then how do we prove this? I mean, if we can't do the work, if we can't just like go backwards and do the complete the square thing, how are we supposed to do this? Well, there's actually a really easy way of proving the quadratic formula. Now, I guarantee you, this method of proving the quadratic formula works is going to be far easier than going through all of the nasty work of inventing the mathematics yourself. Listen, this problem gave you the answer. They told you what z was. That's quite the luxury. A lot of problems, they won't even tell you that. They'll just say, find z and prove that z is z. Figure out what it is and then prove that that's what it is. Luckily for us, we're given z. Now, because this object right here, I want you to think about it as an object because it's being defined in a very special way. It's either that or it's this if that number is negative. So it looks like there are two possible scenarios that we can bump into. Either that number is negative or it's not. So let's work out the first case. Let's start with b squared minus 4ac is greater than or equal to 0. So that means that this square root here makes sense. The input is non-negative. Now, if you want to define the square root function over the complex numbers, you have to do this weird, like, helix twist thing to create some Riemann surface, and then you can define the square root in a way that makes a little bit more sense. But we're talking like at least 100 videos from now, so we won't be covering that for some time. Okay, so b squared minus 4ac is greater than or equal to 0. Now, I should have mentioned in my proof that my assumptions were right here. So that right there should go right in my beginning. My bad. All right, so case 1, b squared minus 4ac is greater than or equal to 0, so that I can actually make sense of what that means. That's great. How do we prove that I have my two answers here? Well, a good way to know if your answer is correct, if you have your answer, they gave it to you, how do you know it's correct? You plug it in. That's it. And you see if you get 0 as a result. So let's try it. So something important about quadratic polynomials is that there are exactly two roots. Exactly two roots. You can't get 3, you can't get 1, you get exactly 2. This is a result that I am not proving in this specific video. So I'm not going to prove that there are exactly 2. I'm just going to show that these two roots here are actually roots. That if I plug those two values in for z, then I should get 0 as a result. So let's try the first one. So let's let z equal negative b plus the square root of b squared minus 4ac all over 2a, which is a real number because b squared minus 4ac is non-negative. And so now I can just plug in z and see if I get 0. All right, so now I have az squared plus bz plus c, but I just replaced z for what z was. And hopefully I get 0 as a result here. Now, a is non-zero, which means that these values here are all real numbers. They all work still. So to be careful now, if I were to square that a, that would be an a squared. And so the a would only cancel with the squared part. And so we would still have an a in this denominator. Let's keep going. So with this square, I'm gonna do some foiling. So negative b times negative b is b squared. minus b times the square root minus 2 times b times the square root of b squared minus 4ac plus b squared minus 4ac all over 4a. And now I'm going to want to eventually add fractions here. So this denominator I'm going to want to be 4a, considering I have a 4a here. And so the common denominator between all three terms here is 4a. So I'm going to try to get these fractions to have a denominator 4a. And to do that, I need to multiply the denominator by 2, which means I need to multiply the numerator by 2 as well so that I don't change the value of that number. So this simplifies to that if I get the denominator to 4a. And then the plus c, I'm going to have to write down here. So plus 4ac all over 4a. Because this would simplify to just c. And keep in mind, a is non-zero, so I can do this. Okay, so let's simplify this. Now that we have every fraction with the same denominator, then adding across numerators is pretty straightforward. So let's cancel some things. For example, b squared plus another b squared, but then minus 2 of those b squareds leaves you with 0 b squareds left. 2b times the square root of b squared minus 4ac minus 2b times the square root of b squared minus 4ac is just 0. And so I'm just left with negative 4ac all over 4a plus 4ac all over 4a, which is 0. And so we did it. Az squared plus bz plus c is 0. I showed you it's 0. It works. I know you might be thinking, wow, this looks crazy and everything, but this proof allowed me to avoid having to find the solution by hand. Now, you should know how to find the solution to the quadratic formula by hand using the method complete the square. But when it comes to writing proofs, you have to understand when you're using circular reasoning and when you're not using circular reasoning. And starting off your proof by saying that az squared plus bz plus c equals 0, that's circular reasoning. You're assuming your conclusion right off the bat. And then you eventually show that, hey, it works. Everything's good. 1 equals 1. You end up getting like a tautology or something. So it's important to know how to structure a proof, especially relative to how you would go about these types of problems in high school and college. All right, so are we done? Well, not quite, because we only showed one solution. We didn't show the other solution worked too. There are 2 solutions. Keep in mind, that's an assumption we get to make in this proof. And so we found one of them. And so how would we find the other? Well, we just plug that in too. Now, instead of going through all of this again, I'm just going to edit this. So now we need to check if this solution works as well. So what if that was a minus symbol? Would that mess up anything? Well, yeah, that would be a minus, that would be a minus, which would mean that's a minus, and so is this, which would make that symbol a plus, and this symbol would be a minus symbol, and so they would still cancel out, and so everything would still work out. And I really don't want to write that much math again. But you can use your imagination and just assume that that was the other solution. But technically, we're still in case 1 when b squared minus 4ac is non-negative, so that the square root of this thing makes sense. But we haven't done case 2 yet. So let's do case 2. But again, I'm going to do it in a way that doesn't require me to write all of this out again. Because case 2 is really similar to case 1. It's just when b squared minus 4ac is negative. And so instead of doing the square root of b squared minus 4ac here, we would define the discriminant to be I times the square root of negative b squared plus 4ac, so that the inside of that square root is guaranteed to be non-negative so that you can take the square root still. So everything in this definition still works. They handle the special cases when the square root is negative, which is good. All right, so now we're looking at negative b plus I times negative b squared plus 4ac. And so this problem changes a little bit. So now I have an I here. That turns to a negative and that turns to a positive. Put another I there. Turn that b squared to negative and flip this sign to positive. And then we can just keep going until we can't anymore when we actually have to FOIL. But that's okay because we just saved ourselves a bunch of time. We only have to write the last bit of this proof here for case 2. So I'm going to FOIL this numerator out. So that's what I get when I FOIL out that numerator. The denominator is still 4a. I'll write the second fraction below. And I'm going to turn this denominator into 4a by multiplying both the numerator and denominator by 2. And then for c, we're going to want a common denominator of 4a. So I'll rewrite c as 4ac all over 4a. And again, a is non-zero, so I'm allowed to make all of these moves with a. And now we simplify. So I have a b squared here. And then I squared times negative b squared is just positive b squared. So I have 1b squared here. That's 2b squareds there. Total. Minus 2b squareds. All cancel. Here I have I squared times 4ac. Don't forget the distributive property applies to both of these objects. We'll get to that though. Here I have negative 2bi square root of negative b squared plus 4ac. And here I have positive 2bi times the square root of negative b squared plus 4ac. They cancel. And so what am I left with here? Well, keep in mind that 4ac is inside parentheses, which is being multiplied by I squared there. So that's not just 4ac, that's 4ac times I squared, which is negative 1. So I'm left with negative 4ac all over 4a plus 4ac all over 4a, which is 0. And there we go. So that solution works. So if the input of that square root is negative, the discriminant part, if it's negative, then we can redefine the solution. And we really don't have to do that much. We just have to introduce an I into our formula. And so that's the proof that the quadratic formula works. We checked it. We checked the solutions. The solutions work. We get 0 as a result, and I didn't have to assume my conclusion at the beginning of this proof. Anyways, thanks everyone, and I'll see you all in the next video.